All right, so we should be back. Howdy, howdy, howdy doody. So I'm wondering if I should lower the gain on my microphone here because I'm kind of yelling into my mic. Yeah, I think it's fine. I think yeah, this should be okay. So hello and welcome. We're here again with another question. The other question we did it relatively quickly, so I'll go ahead and we'll get right into this one. That was exciting, man. I like that. I like when you can do questions quickly. It's cool. That's fun. It's satisfying. So House Robber 3. So this is similar to questions I've seen before, I believe. However, we'll see how this goes. I don't know. I mean, this could we get stumped or not. I don't know. We'll find out. The thief has found himself a new place for his thievery again. There is only one entrance to this area called the Root. The Root. Besides the root, each house has one and only one parent house. After a tour, the smart thief realized that all houses in this place forms a Oh, really? Okay. Fair enough. Fair enough. It will automatically contact it meaning who, somebody will automatically contact the police if two directly linked houses were broken into on the same night. So it being the neighborhood itself has been set up in such a way. The alarm systems in the neighborhood. Okay, so the alarms just it. The thing will automatically contact the police if two directly linked houses were broken into on the same night. Determine the maximum amount of money the thief can rob tonight without alerting the police. Okay. Alright, what does it mean if they're directly linked? Alright. One and only one parent house. Okay. After a tour, the smart thief realized that all houses in this place form a binary tree. Maximum amount of money that the thief can rob tonight without alerting the police. Alright. Contacts if two directly linked houses were broken into on the same night. What does that mean, directly linked houses? I guess that means if one is a parent of the other, I suppose. It's a red-black tree. Oh, that's another question at some point I gotta go over is like implement a red-black tree. Right, that was a question I think some engineer got like years ago, and I was like, oh, I would get stumped on that if they asked me that. So I'll have to go over that at some point. Okay, maximum amount is 4 plus 5 is 9. So really, this is actually not as hard of a question as you think. This ends up being, I think this ends up being, maybe I'm wrong, but I think this ends up being the odd or even sum. So there's either take the sum for every node at the even depth and take the sum for every node at an odd depth. I'd take the maximum of those two. I want to say that's related to this question. I could be wrong about that, although I don't know. There maybe are cases where, I don't know, you'd probably have to prove that if that's the case. I don't know if, first off, I don't know if that's the case. And second, I don't know if it's even more efficient to do it that way or to do it in a more general way. Let's think about this for a minute. Well, the thing is, if we take a node, we can't take its parent. And the thing is, we can always take the siblings, right? That's no problem. However, you may not want to take a sibling because the children of that sibling are much better. So in other words, if this was 2 and 5 down here, you would actually want 5, 2, and 5. So no, it's not going to be every even or odd. That's not what you want. Yeah, you do want, basically, I guess you would say for each parent, you want to decide either you have the parent or the two children. And the thing is, you don't pick, well, I don't know. I actually don't know. I think maybe, it's hard to tell, huh? What would be how do you do this? I don't know. I want to do it in linear time. Let's think of a way that we could solve this. It's not linear. That's like just some naive solution. Let's start with that. So something naive would be basically every possible permutation of, not permutation, but what you could do is you could do like yes or no question for every node, which would give you an exponential time algorithm, which is extremely inefficient, or probably extremely inefficient for this problem. And basically each yes or no is like a 0 or 1 or on or off, and you basically have 2 raised to the number of nodes choices, and for every possible set of choices you basically can calculate the sum from the value at each of these nodes. And then so it's basically like dumping all these nodes into an array and then deciding sort of to randomly pick nodes in the array. Not randomly pick, I'm sorry. Go through all the possible, it's not permutations, it's combinations of the nodes in the array. Is that right? Or in values in the array. It's combinations. It's not even combinations, it's because combinations would have even yeah, I mean combinations of node selections. Yeah, it's actually slightly better than, it's still exponential time, but it's slightly better than 2 raised to the n. Actually, no. Wait, why wouldn't it be? Why did it just no 2 raised to the n? No, 2 raised to the n is better. No, it's 2 raised to the n. No, what is it? Wait. It's not combinations. It's yeah. Well, I mean, it's checking it's brute forcing every sum of every subset of the elements. That's what it is. Yeah, that is 2 raised to the n. Yes. Which actually, oh no, I'm sorry. Yeah, because all the combinations is, when you count all the combinations, that is the number of subsets. Okay, yeah, right. Okay, never mind. That's why I'm getting confused. I'm like, wait a minute, why something's not adding up here? Yes. Yeah, it's all the possible combinations of these elements of these nodes and their respective values, and then you would find the sum, the largest sum of all of those. Now that's a pretty inefficient way to do things. You can do it that way, however, it's extremely inefficient. So and on top of it, you would need to remove, you would filter out the sums that are linked to each other, I guess. So their relative positions would matter. You'd devise some way to check their positions, and so some of these sets would just be automatically disqualified. So what do we do? How do we do this? So the maximum sum overall possible without disqualifying anything would just be the sum of all the numbers, which is the sum of everything. So there is some kind of greedy aspect to this, certainly, that we can take advantage of. I want to say that there's an element of like dynamic programming that we can do, where we have like different choices that we make in the tree, something like that, and we can kind of recurse. And I guess we would say if we chose 3 or not, there's a summation that we can get. And the left subtree, we wouldn't be able to choose 2, we wouldn't be able to choose 3, and we'd have to get the optimal sum without choosing 2, without choosing 3. And then so I guess the choices you have are something like, just thinking like what is like another way to do this? You could say you could choose 3 or not choose 3. If you choose 3, then you can't choose 2 or either the 2 children in the next sum. So you can actually basically enumerate all of the children and get the optimal sum, recurse on all of the grandchildren. The optimal sum of all the grandchildren added together plus 3, or you can have the optimal sum of the two children added together, right? The recurse on the two children. Yeah. So if the grandchildren plus the grandparent, that recursion, or the two grandchildren, or two children, recurse on those two. And for null nodes, if the grandchildren are null, if the node itself has no children, so the children would be 0 and the grandchildren would be 0, and so this actually, yeah, so we don't even need to worry about. Okay, kind of interesting. So let me try something. So let's give this a shot. We're gonna go recurse. I just call it. I don't have anything particularly. The name, I just kind of give it like an arbitrary name. So tree node R, and we're going to say return recurse. Excuse me, of R recurse. Auto F, return an int, and we're going to do something like base case if not R, return 0. Otherwise, we're going to say int val equals R val, and we're going to say return the maximum. So we want int children sum, which is f of R left plus f of R right, and then int grandchildren sum, which is going to be four values plus 4 recursions plus val. And the thing is, this is going to be R left. Now we have children, so I want to say something like grandchildren. I want to do this in a way that makes sense. Oops. Grandchildren sum. And we're going to say if R left, if not R left, then push back null pointer. Otherwise, and then same thing here. If R right, otherwise push back R right. And then now we're going to say, starts off at value, say for auto X in grandchildren. P, we'll say, or just C. We'll do it this way. We're going to say grandchildren sum plus equals f of CF. Okay. Now, the thing that's kind of tricky here is this is kind of ugly. This is like a lot of extra code just to, basically we're trying to make sure that if there aren't children or if there aren't grandchildren, that we handle that correctly. So we take the maximum of the children's sum and the grandchildren sum. And this should be correct, basically. Let's just see if this executes. And oh, root. And oh, yeah, also this is tend to miss that typo. Okay. So yeah, this will give us at least the right answer. However, what the runtime complexity is for this is a totally different question. So I don't actually know what the runtime is. A few things to say. I don't know what the runtime is, and I don't know. There were some other thoughts that I had too, which I forgot. Oh yeah, I want to clean this up. This is really ugly. Two things. One, I believe it's correct. A few things. One, I think it's correct. Two, I don't know how efficient it is. We would want to modify this so that's efficient enough. We kind of want to figure out what the efficiency is, because it might actually be efficient enough as it is. And three, we want to know if we can clean this up. If it's efficient enough, then we can clean this up, and this looks nice. We could probably clean this up right now, but the efficiency, so the reason I think it might actually be a lot more efficient than we realize is because if this and this, if we say it takes time linear to the number of nodes, which I think it is, then this is half of the nodes and this is half of the nodes. So it'll take linear time to calculate this amount. And then the grandchildren are going to be a fourth of the nodes, at most, a fourth of the nodes, a fourth of the nodes, a fourth of the nodes, and a fourth of the nodes. So it'll take a linear amount of time to calculate the grandchildren's sum. So if it takes linear time to calculate children's sum and linear time to take the grandchildren's sum, then it takes overall linear time to calculate the root. Hopefully that makes sense. It's time proportional to, a constant proportional. Now the thing that's tricky is that may not be totally correct, because you could have a situation where, like, even though it's a linear amount of time, in these cases, if there's some constant that we're dealing with, and that constant multiplies as you have more layers, then I guess you have this multiplication, which could make it quadratic, right? If you have 2 raised to the logarithm of n, that's log base 2 of n, that's n times. So I'm actually not sure if this is quadratic or if this is linear. I don't know. I do not know. I know that you could potentially memoize this function, so that way when you calculate the parent and then you calculate the grandparent, or the child and the grandchild, you're not calling these functions again on each of these nodes. You call it once per node. I think this is, if we memorize this, I think it's definitely linear, because we could say that if every function call at the base is constant time to calculate, then that means you're calling this function once at every node, and after that point it's going to be constant time every time you call it. And so if these are constant time calculations at the root, then it's actually constant time at the root. And so we know that basically we would say there's one call for every node, and it's after that it becomes constant. So actually it's just a constant call at every node, which gives you linear, because you're calling this at every node at least once, and at most twice, right? Something like that. Something like that would I think. So let's memorize it then. Let's memorize it before, so don't feel too uncomfortable. All right, does that work? Okay. Let's try a few cases. I think memoized, then this is going to be linear time. And can we try some test cases that are kind of awkward? All right, let's see how we do. Oh, the last two cases, I guess, don't make sense. We're gonna go for it now. Hey, we're right. We did it. Correct. Sweet. Not bad. How much time we take? 20 minutes? Not too bad. Okay, sweet. So now, all right, it's efficient enough. Not extremely efficient, but efficient enough. Used a bit of memory. I want to know if we time out now, if we don't memorize this. I was curious about that. Actually, we don't need to delete everything. We may need it. Excuse me. I don't know what's going to happen here if we do it this way. I think it's quadratic time if we do it this way. I think it'll time out. All the memoized parts we'll just remove. All right, let's go for it. I think with TLE in some cases. Yeah, okay, so it is quadratic time. Yeah, that's what I thought. I was like, I don't think it's actually going to be fast enough if we do it without memoizing. Okay, let's put back the memoized portion. Let's run our code. Let's try again. It's relatively slow. Relatively slow. Because it looks like other people have much faster solutions. So we'll look at the other solutions, the ones that are faster. And okay, let's modify these pieces here. So basically, we want to optimize this portion. So we want to say you could do it this way. You could say if r left, then if r right. Okay. You could do something like this. And what is it? Does this still give us the right answer? Sorry. I made a mistake. Yeah, we should still be able to get the right answer. It's just to modify this a little bit. Okay. There we go. All right. How do we do here? Okay, that's a lot faster. Yeah, that's way faster because we were creating this vector in between, which we really didn't need to do that. And don't really need this either. Well, wondering if there's like, just looking for things we can do. So we can set this to the children's sum, and then we say if ret is less than grandchildren's sum, then set that to the grandchildren's sum. Grandchildren. That's slightly faster than the max function, calling the max function call. And then so 12 milliseconds. And then we can actually can remove this altogether. Excuse me. Okay. And then I don't really know how we can change this to make this faster. Yeah, I mean, this is probably as well as I can do it. It's kind of all I got. I think this is all I got. You could maybe give the root nodes an index. Possibly, I don't know about that. And then you can use a vector instead of a map. Not sure about that though. Nah, I think that's all I got. Let's see if we can find a way we can do this more efficiently. My thinking is maybe if I just keep running this over and over again, I'll get the 100%. And also about the memory. I don't know how do people use less memory than this? How did they do that? Oh yeah, there you go. Yeah, I bet if I keep running it, I'll get there. Okay, I think if you, let's see the discussion. Yeah, I'm curious. So this is not too bad. This is not too bad. This question. Kind of a simple, memoization question. DFS, C++, 1 millisecond Java, DFS solution. Interesting. I have to look at that. A DFS, okay. Oh. Huh. Oh. Yeah, I like that a lot. Yeah, that's good. Let's do. Oh, didn't mean to do that. Let's look at. Okay, let's do that then. Yeah, I guess. All right. You don't need this. It's memoization. That's not necessary at all. Huh. Okay. Left sum, right sum. Okay. And return an integer. So I guess you would say, let me think about this. So I kind of briefly looked at those answers, and basically what was suggested was to return multiple values, which I did that for another question, another problem, and that worked pretty well. So what you can do is return the maximum value of the left subtree and the maximum value of the right subtree. And you've got to decide if see, the thing is okay, I think I understand. So you've got, you have 5 numbers and you have 2 numbers. You have the maximum value you can get for the four subtree. No, I think the way that I'm thinking about it is different from the way that he thought about it. You can do all the grandchildren added together, and the grandparent, or you could do the parent, the 2 parents, whatever you get from recursing on the 2 parents. That's what I did here. However, I don't know. I think I need to read their solutions again to understand what they did. Let me think about this. Excuse me. I don't actually understand. What do they do? How do they do this? I don't think so, man. I think this is inefficient if we. I don't. I guess we have 3 different numbers that we're keeping track of at each point, which is the left subtree, the right subtree, and the value at that node, I suppose. Or the maximum for that particular node. I guess this isn't as hard as. Yeah. Okay. I think I understand. I think I understand what to do. So we're gonna do something like the following. We're not gonna memorize anything either. I'm gonna get rid of that altogether. I think I get it. So you call f of left, and you have int left l r. Excuse me. You have right left and rr. Actually like how we did that way. So root, or call it x. Okay. So yeah, these are initially 0 to begin with. So LL and LR, and then an F. And right is RL and RR. And what we want to return is the maximum. We do the same thing we did before, where ret is going to be X value and plus, or rather, let's do left and right. There's left plus right, and we say if ret is less than, or I mean, just do this too. Something like this. And oh, that's kind of interesting. So we set the return values right here. We don't even need to set integers. You just set them right here. Yeah, this is really interesting. So there's like a few things here. So I guess the first thing is this correct? And the second thing is, we're returning a lot more information per call, and we're using that information, and that's how we're making it more efficient, because we know that this actually will only traverse the tree and visit every node once, so we know it's linear time. However, is this correct is the question. And I think it might be. And we don't really need, we don't really care what these are. It's actually, I don't know if that matters. Yeah, looks like it doesn't matter. And I'll explain in a second. It's like a really clever way to do this. Let's go for it. Hey, there you go. Okay, that's a lot more efficient, a lot less memory. There we go, sweet. We don't care about that. So I think this is just, yeah, it's correct, right? Done. Super efficient way to do that. Wow, that's amazing. That's so cool. And we just want, what about this? Okay. Less memory. And we want, there we go, really fast. Can we get 100%? Oh, we're so close. Attempted too soon. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Ah, not quite. How do we go faster? I don't know. How do I go faster? It's got to be a way. I don't know, man. It's pretty good though. I guess if we didn't write this subroutine, if we wrote it right in here. I don't really know. I don't know. It's pretty quick though. It's fast enough, you know, fast enough for us. 4 milliseconds, really good. Yeah, so, okay, so the key though is, we really don't need the rest of these. It's probably fine. So there's something to learn here. There's more to think about, more to talk about. And that's particularly, so yeah, we came up with a solution and it was somewhat correct. However, it looks like, yeah, if you sort of return more information from each call, you can make things a little more efficient, I guess, instead of trying to memoize things using an unordered map. So basically, so I don't fully understand this solution quite yet. Also, I should mention that. So what we did was we said, okay, we're going to return the solution for the left subtree and the solution for the right subtree in addition to the solution for this node. So the return value for this node will be, you know, whatever it is, and then also we're going to return the left and the right. And we're going to do all this recursively. And the way we do it is we literally just take our left integer and run recursively on the left subtree and run recursively on the right subtree and get those values and then set them and return them, right? And also we have 4 values that, you know, give you sort of the grandchildren. And so we have the solutions for the grandchildren as well as the children, right? And we get the grandchildren solutions for free because we are already saying, all right, we want to get the left and right subtrees. So we sort of push that information kind of comes for free. And by design, and then we say, okay, our return value for this tree, for this solution is going to be either it's going to be the left and right subtrees as they are, right, the optimal values for those two added together, or it's going to be the root node plus the optimal values for the grandchildren, right? And those are the two possibilities to pick from. You take the maximum of those two. And it seems that we actually, it's slightly more efficient to just return B here, by the way. Excuse me. Yeah, just ever so slightly more efficient to do it that way. Just kind of funny. That was why we weren't getting the 4 milliseconds before. There's got to be like one slight efficiency that we can do here, and got to be something we can do. I want to say. There's got to be something we could do here. There's got to be a way to just ever so slightly optimize this. What could it be? I don't know, man. We're so close too. There's gonna be one tiny little thing we could change to get 100%. Get 0 milliseconds. By the way, it's like really unnecessary to optimize it this much. It's just, I like to. I just like to know these little tricks you could do, small things you can do. I don't know, that's good enough. Let's not go crazy. But yeah, that's really interesting, this approach. I didn't even think to do that. So yeah, I'll think about that more in the future for what do they call that? Yeah, depth first search type questions where you can actually get more information out of the function call and use that to your advantage. Like that really lends itself to this problem, that kind of a technique. It's not something used very much. All right, so I learned something new. So that's pretty neat. So yeah, thank you all for watching. That's a new thing we learned. So that's why we do these. So there we are. I'm gonna head off. Yeah, thanks again for watching. Talk to you soon. And I'm gonna take a few minutes to kind of relax. And yeah, I mean, we learned something new. So, all right, I'll be back. Take care.